Yes, we can hear you.
Okay, great. So thank you once again for joining us. My name is Lucy Montanaro, and I'm the Pharmacy Education Advocacy Coordinator. I am from the United States, and I am here to present Pharmaceuticals and the Environment. This is in collaboration with FIP and IPSF, and our speaker will be Eva Tarasalmi. And I would just like to ask all of you to please type in what your name is and what country you're from, just so our speaker has an idea of who will be joining us today. So, okay, well, everyone introduces themselves. I'm going to move forward and introduce IPSF to those. So IPSF is the leading international advocacy organization for pharmaceutical students and recent graduates. We promote improved public health through provision of information, education, networking, and a range of publications and professional initiatives. And I am part of the Pharmacy Education Committee, and we try to bring as much information as we can to our students, information that we believe will help them grow professionally. Sometimes this information is something that isn't necessarily taught at universities that we believe will help them grow as professionals. So we do provide internships, webinars. We do have our Young Researchers Forum, which we hope you will all check out. And we also have educational and scientific poster competitions and pharmaceutical science initiatives. So please check out our Young Researchers Forum if you have a chance. So for this webinar, I would like to go over some instructions for us all. In order to have a successful webinar, please mute your microphone at all times. Once again, please introduce yourself in the chat box with your name and country. And as our speaker is presenting, if you have any questions throughout the webinar, please type them in the chat box during the presentation. And at the end, we will have time for the speaker to answer them. And I will be sending out an evaluation form. If you could please provide us some feedback, I will email it, and I will also type it in the chat box at the end. Without further ado, I want to present our speaker. Her name is Eva Tarasalmi. She has an MS in pharmacy, EMBA, and she is a certified coach as well as pharmacy owner. She is also the FIP vice president. She has worked on a project called Generation Green. She is from the Helsinki University Pharmacy, where she is a faculty member. She has also written a Green Pharmacy Practice reference paper and statement in FIP, where she is the co-chair. She has also done numerous presentations and publications in sustainable pharmacy in international and national conferences since 2015. So we are very excited to have her here, and without further ado, I will give her the floor. Go ahead, Eva. You can introduce yourself.
Thank you so much. We can take the first slide and start this seminar. Okay, today we are going to talk about the effects, what the active pharmaceutical ingredients do have in our common environment, and about the mechanism, how they enter in there, and how we can work together to diminish this problem, which is quite a big one, in fact. And the first part of this presentation we're going to have today talks more about the active pharmaceutical ingredients, about the pharmaceutical residuals in the environment, API sources, why do they accumulate, what can we do in the wastewater management, how do the APIs affect in the different environments, what are their effects on human and animals, and how to evaluate this environmental risk what an API can produce. So this is more of the theory. And the second part, then, there we will discuss more our role, what we can do as pharmacy professionals, and how we should be educated to understand these problems. So we continue. Next slide, please. So an active pharmaceutical ingredient, the real molecule behind the effective medicine. So we can see here in the left side of this slide, we have the toxic chemicals, and we have the APIs, and then we have the biologically ineffective chemicals. So if we have a biologically ineffective chemicals, we have 100% safe molecule, but unfortunately without any effect in our bodies or animals' bodies. And if we have a very effective, biologically effective chemical, it can also be very toxic, but then it's not usable even as an active pharmaceutical ingredient because it's only toxic. So our APIs end up in this middle of this picture, and if we look at them, so the whole idea behind being an active pharmaceutical ingredient is that it has an effect in our bodies, otherwise we couldn't use it as a medicine. And this same, that it has an effect on the biological system, means that it also can have an unwanted effect where it ends up in a wrong place, so to say. And this effect depends on the type of exposure, whether it has been exposed in a chronic way or an acute way to the environment. Also the biotransformation of these APIs has a effect on what kind of effects they do have in our environment. They can be degraded by the sun, for example. They may have some interactions together with the other APIs, so we don't really know what will happen in this cocktail. There are also these molecular interactions, and the problem also might be that these APIs concentrate in the food chain. And then I have mentioned here the analytical chemistry, because that has also developed so much in the recent days that we have a much better possibility also to find these APIs in our environment than the case was before. So we have today about 3,000 molecules and other ingredients, which we count as being APIs, and these are the molecules we are talking today. Next slide. Next slide, please. Okay, so I have 3 different slides here about how the APIs end up into the environment. The first slide shows here on the left side, we have the consumers, we have the pharmaceutical industry, we have the hospital usage, and we have the agriculture. So the medicines are used in all these environments, as we well know, and they don't vanish anywhere when we use them. So we are not talking about the medical waste, we are talking about the normally used medicines here. And through this usage, and our bodies try to get rid of them by metabolism, as we all know. So these water treatment plant, when they go to our body and then to the toilet, etc., they can go direct to as waste to the wastewater, or they can, through the agricultural use, end up in the sludge and manure on that way. And from these sources, they continue their way, and they may end up through the wastewater management plant to our drinking water. They can also end up to the surface water and groundwater. And when this sludge or manure is used as an agricultural fertilizer, it can end up in the agriculture. And in the next slide, we see how big these different sources are. So as we can see here on the left corner, we see the industry, and down there there is the usage. So the normal usage, as you can see from these fletches, how big they are, we can see then the amount of the problem. These leakages from the industry are much smaller problem than this just normal usage. And also this waste is a smaller problem than a normal usage. And in this last slide, concerning this thing, in the next one, we see this same thing presented, but now we have all the sources where these medicines are used, and also this how they end up in the water from the different sources and from the farming, and then through the industry and normal usage, where this how this flow goes on. So if we then look at the next slide, what are these residuals in the environment we can see? As I already mentioned, they are biologically active transformation products of these active pharmaceutical ingredients. But we also, as we all know, as pharmacists, we also have the additives in the medicines. So also those can be biologically active in some cases. And what we can find in the environment, there are the residuals of the antibiotics, of analgesics, of lipids, beta blockers, cytostats, hormones, fat-soluble sustainable molecules are a specific problem, and then the molecules which can accumulate in food chains. And why these are the things which we can especially found in our environment, I have tried to explain this a little bit in the next slide. This is where how the metabolism of APIs happen in our bodies, as you know. I think you all in your pharmacology course have gone through this. So what happens is that our body, through the mechanism of glucuronidation and a sulfatation, acetylation, etc., tries to make the molecules more water soluble so that the body can then get rid of them. On the left side of this picture, you can see what happens to the acetaminophen, paracetamol, as we know. So there is the glucuronidation, there is the sulfation possibility, there is this dehydration process, and which then ends up in the glutathione conjugation. And these metabolites might cause different troubles than the original problem. And this is one very important issue to understand, because when we are analyzing the residuals for example, in the wastewater, so we normally are analyzing the molecule itself, not the metabolites. And this is a big issue. We are today very much discussing that how we could be able to really measure the amount of the metabolites as well, so that we really know what is happening here in this issue. Next slide, please. This metabolic effects has some effect on this measuring, as I have tried to explain here. We see in this picture that when we are measuring the amount of carbamazepine and how it's metabolites and the molecule is found in the wastewater. So we can see that when we start the process, it seems to be there seems to be a smaller amounts of this carbamazepine in the influent, but in the effluent we can find more of the molecule, which is quite interesting. And this is due to the reason that this how it has been metabolized from our bodies. This sugar molecule here, it comes out from the carbamazepine during the wastewater management, and as a result of this, we see more of carbamazepine in the effluent water than we see in the water which went in to the wastewater management. Next slide, please. So what is happening in the wastewater management process? This picture is from a very big wastewater management plant in Helsinki region, and it's a very typical process what they do have there, but possibly a little bit more effective. And we know that possibly it is, or it is possible to get rid of all the medical waste during the processes in the wastewater management, if we add to the end of this, say, this normal process, so to say, some osmosis or this kind of a mechanism, but it's very expensive. And that is the problem, that we have to do some balanced decisions, that how do we act with this, and what are the effective means of a, or most cost effective means of getting rid of waste, medical waste. Anyway, so the process here is mainly that you start with inlet pumping station. You screen first these bigger things out from there, and you have the first grit removal. Then you start to aerate the mass there, and you have the primary sedimentation after the pre-aeration. You add also ferrous sulfate, which is the main active ingredient what you use in these processes to get rid of the sediments. You take even this raw sludge to be processed forward, and during that process you can get a biogas, and you can get use that for a gas utilization, and you also get this sludge which can then used afterwards for agriculture. And if we look forward after this primary sedimentation, there is a second aeration, and you add also some nitrates to help these microbes here to do their work. You get to the secondary sedimentation point, where you collect more of the what can be used as sludge. And then you have the biological filter processing, and then you have this outflow tunnel where the water goes out. And if we look at the next slide, so we can see what happens to aphids when they go through this mill. So they can adhere to the tenor, to this soil. They can further be biotransformed or biodegrade. There happens oxidation and nitrification processes, and sometimes some byproducts might be produced. And the problem here is that not all active pharmaceutical ingredients react in the same way. So it's quite difficult to calculate really what happens in the different phases of these processes, and how different molecules are what happens to them. And as I already mentioned, also these metabolites should be considered when we discuss this process. So I will, in the second part of this presentation, give you some solutions, but now we go through this what happens, and the next slide shows us that when an aphid ends in the environment in this wastewater, so what kind of effects it could have. And this is an article from Environmental Science and Technology, and tells about the irrigation of root vegetables with treated wastewater. So what we can see here is that the wastewater treatment plant, the water comes from there. It's used for the irrigation. We have this root, in this case the carrot here, getting in these molecules, this water and the molecules in there, and then it's gone to the consumption, and unfortunately then we are eating these molecules in there, and through that it goes again to this cycle. So these molecules don't vanish anywhere. They transform, continue they way in the cycle, and we don't really know what kind of effects they can cause. In that next slide, this is even more evident. So this example comes from the pharmacology, and we all know the molecule tramadol, the product, and Some years back, the pharmacognostic researchers were very happy to find out that they have found out that this Nuclea latifolia, which you can see here in the right side, could produce. They had found out that there was a tramadol in this medical plant, and so they came to the conclusion that this plant could produce tramadol, and that was of course a huge invention. Everybody was very happy. But then they started to think again on this, and what caused the thinking was that that was only, it wasn't the racemic a product what they could find, or it was only this one form of tramadol, and they could find out that that was the synthetic tramadol, what they had found in this plant. So what really had happened was that the people who were taking care of these plants have been treated with tramadol, and they were peeing outside, and so this tramadol direct from their bodies went, and these flowers, these plants used this, and of course it accumulated into these leaves. So in fact, what we were seeing was a fully synthetic tramadol in these plant leaves, instead of this fantastic idea that these plants could produce this themselves. So these kind of things can happen. In the next slide, we can see where the apis are detected. And as you can see here, the bigger is the usage, the more we can find apis. Unfortunately, this doesn't mean that these green areas in this map are free of apis. This only shows that where you have made these measures. So we can say that the apis are nowadays everywhere in our environment. The good thing here is that the concentrations are normally very, very small, but anyway, they can be everywhere in our environment. This, by the way, these colors here doesn't show the concentrations. They only show the number of pharmaceuticals detected in surface area, or surface water, or groundwater, or tap water, and drinking water. In the next slide, there is a list about the most common apis found in this analysis. So the leader, number one, is Diclofenac. Unfortunately, a well-known problem for a environment. The next one is our friend carbamazepine, which we already discussed. Third one is ibuprofen, and then the list continues. You can see there are many hormones and many antibiotics also in this list, together with the NSA IDs. And if we then start to look at what kind of effects these apis might have in our environment, so we take the next slide, and as I already mentioned, so our main problem is the biological activity, which is needed to make a good medicine. And of course, we never want to get rid of the good medicines. The most important thing is that we have good medicines, and for this reason, we have to find ways how we can get rid of the problems these medicines caused in their second life, so to say. But if we look at this picture, we can see it could be a little bit bigger. I'm sorry for this; it's very speedy, this one. But we can see that there are different animals and the different causes what these molecules have caused in them. And in the next slide, I will have some more examples, which are more not that busy than this one. You can study this more afterwards. So we can start to discuss about the biggest problem possibly today, which is the antibiotic microbial resistance. If you take the next slide. Yes. So we all know that the AMR is the only medical issue which has taken into the list of the United Nations sustainability problems or the goals, and the antibiotic resistance is really a problem which will, in the worst case, cause the situation where we couldn't have any effective antibiotics in our usage. And if we think about this, how this problem is produced, we can clearly see that this environmental issue has a big role here. Most of the antibiotic facilities, production facilities, are in India and China, as most of the other API production units as well. And as we all know, the GMP doesn't cover the wastewater management. The wastewater management or leakage management is covered by the national environmental legislation. And unfortunately, in many cases, these legislations are not in place in the developing world, which causes the problem that if the factory is very good in a GMP way, it might not be that good in its wastewater management part. And when this untreated wastewater ends up into the river somewhere in India, let's say in Hyderabad, it can cause so-called pocket, where these resistant bacteria to these antibiotics, which are ended up in this water, start to grow. And these resistant bacteria, they can then end up from there to all over the world, and they cause this antibiotic resistance to spread around very quickly. And we of course have also the problem of the misusage of antibiotics. We know that even the pharmacists in many parts of the world still sell to their patients and their customers antibiotics without prescription. So, and if we want to be part of the solution and not part of the problem, that's a practice which should stop immediately. So in the next slide, I will show you this as a table. So we have about these 200 antibiotic production facilities. It has been estimated by WHO that about 30,000 to 70,000 tons of waste, which antimicrobial activity is generated by these industries. And it's in liquid form in most cases, so it has to be treated before it's released into the environment. And if this doesn't happen, then the environment might be polluted by this water, and then we are in this problem I already described to you. There is of course a cost to do this treatment, and it has been calculated that it's about 50 cents per kilogram of active ingredient. And this is the price we have to be ready to pay to get rid of this problem. And I don't think it's right that the Western countries with their reference price systems are dumping the prices so that these costs cannot be added to the reference price. I think in this case we have to change our laws and understand that these environmental issues are a common problem, and we have to accept that it also costs something to get rid of this problem. So the next slide, please. Here I have some pictures, and I will not use very much time in discussing this because the time is running, but about the effects what these apis, when they end up into the nature, might have. So we possibly have all heard about these fishes who change their gender when they are when they have been treated with or they have lived in the waters with high concentrations of estrogens residuals, so that they can change their gender. And here we see just a picture about how this happens. So this is a testicular oocyte of a bass, and we see here in in their testicular fibers some eggs being formatted. So this is how these things change. And in the next slide, here we have a small fish which lives in a fresh water. It's Rutilus rutilus, and we can see near the wastewater management units what happens for their intersexuality if they are living in the upstream or downstream sites. And in the next slides, we can see that the problems with mussels when they have been treated with Diclofenac, ibuprofen, or propranolol. So you can see they are not anymore able to fix to the ground where they should then dilute all these things. Mussels are very easily polluted with this wastewater because they are filtering through them a huge amount of water, and then with this filtering mechanism they then get in their body all these wastes. So they are quite good animals to show what is the real level of the pollution in water. In the next slide, we have the effects of oxazepam to fish behavior. So the problem is that these fishes, they should be they should act so that they are afraid of the things which happen in the environment. But when they get oxazepam in their bodies, they start to be very brave, and they think that they can even attack their environment. And with this way, they also lose their lives, and so this is what has been really seen in a real environment, not only in the test environments. And in the next slide, we can see that we can also use this effect that we find all these chemicals in the wastewater management, in the wastewater. So we can also use this fact to measure how much drugs are used in the different countries. So this is a shot from the Scientific Total Environmental publication, where we can see that around the big cities in the European countries, what kind of cocaine or ecstasy or amphetamine or cannabis has been used by these citizens in these cities. So a little bit threatening view. In the next slide, we have possibly the most well-known and what really started the discussion about this, that what effects the apis have in the waters and in the ground. A classic example about the effects of diclofenac for the Indian vultures. The diclofenac was used as to treat the cows. And as you know, when the cow dies in the Indian environment, it's not eaten, and it's left there to be eaten by these vultures. And unfortunately, the vultures don't have in their body any mechanism to get rid of the diclofenac, so it shouldn't end up in them. And when they were eating these cows, which were treated with this diclofenac, so they started all to die. And this happens in hundreds and hundreds, almost the whole population vanished. And then the researchers, of course, became interested on what was the mechanism behind this unexpected effect. And they found out that it was the diclofenac that was accumulating in their bodies, which caused this. And then as the end result of this, these animals are not anymore treated with the diclofenac, but this just shows that what can happen if we don't take care of these issues properly. In the next slide, we also have some figures about the accumulation trends of different molecules to the animals, to the fishes, but they will not go through this in detail. You can come back to this later if you are interested. And Then we discuss a few words about how to measure this ecotoxicity and what kind of tools we have today to understand how this ecotoxicity is measured. In the next slide. So we of course need to have a lot of information about how toxic these our APIs are for the environment, and to concentrate our activities on those APIs which will cause the problem. And to be able to do this, we have to measure the ecotoxicity. And already in 1980s in USA, this ecotoxicity figure became and the ecotoxicity measurements became part of the dossier. When you want to have the sales permission for your product, you have to also in your dossier to give information about how this ecotoxicity has been measured and what kind of results you have got, and then you can make a decision based on this, whether this is too toxic so that it can't be really used, or what are the activities you have to do before you can use it. To EU regulations, this came in 1996. So we have now a guideline on the environmental risk assessment of medicinal products for human use. And we also have a guideline on the environmental risk assessment of medicinal products for veterinary use. And in the veterinary side, the ecotoxicity assessments can also be a reason to say that we are not going to accept your dossier or your but on the human side, it's not possible. So you can never say that a good medicine for some purpose might be denied because of its ecotoxicity. What can happen is that you have to show that how you reduce the problem. But in the animal side, it can be really reduced and said that we are not going to accept your procedure. And the reason is that as you can easily understand, that in the animal side, the animals are going around and they say they are not peeing to any toilets. So the medicine ends up directly into the environment and causes a little bit bigger problem than in this human side. We can see this clearly, for example, in the fish plants, where you are producing fishes in the big tanks in water, and these fishes are also treated with medicines, and the problems are evident for the seawater. In Europe, you also have this REACH system for the toxicity of chemicals, but this listing is not used for APIs, so it's for the other chemicals which can cause environmental problems. And this process of classification has possibly been, for the longest time, it has been used in Sweden with the environmental classification of pharmaceuticals, and with the guidance for pharmaceutical companies, how to measure this ecotoxicity and how to classify the products. They have these A, B, C, D categories for the different products in the market, and these classifications are published in their catalog of the medicines on the market, and it can be used then by the different organizations to if they want to base their decisions of the usage of medicines also on the ecotoxicity. This classification is now used in Sweden and in Norway, and we are here in Finland also planning to see if we can benefit from this classification system. In the next slide, I will just tell you how this evaluation is done. So for the API, there is the predicted non-effect concentration, and you have the predicted environmental concentration. And if this relation for the PEC-PNIC is higher than 1, then you are in the risk if the ratio is bigger than 10, the risk for the environment is big one, and if it's under the 1, it's a small risk, and very small if under 0.1. And this also needs some quantification, because based on your national usage figures, there of course ends up some APIs are more used than others, which means that they can, even if this relation figure is small, but if you use it in a high amount, it can cause bigger trouble than similar number, than with the similar number, but they used less. So that has also been, it has to be understood that this national usage has effects on this evaluation. These systems are developed for active pharmaceutical ingredients, and they come from the general chemical industry. Unfortunately, we don't have any system for the ready-made products, and that's a discussion we are going to also see in the next part of my presentation. So I hope now you have got kind of understanding what we are talking about when we are talking about this problem with APIs in the wrong places in the environment. And now we go to the more optimistic part, which is the solutions. So this is not a dystopia. We are able to find solutions, but what does it cost and how effective the different things are? That's something we have to discuss. The next slide shows that as we all know, the pharmaceutical industry, the pharmaceutical usage, and the whole world of pharmaceutics is global, and we possibly understand it today even better than some weeks before with the coronavirus and the discussions around that issue. So as also these problems are global, and as we saw with the example from the antibiotic resistance, we cannot think that these problems wouldn't or only stay to the hotspots. No, these are, when the APIs end up into the water, they are after a few hours, few days, seen in everywhere in the world. So that's why we also have the global solution models. In the United Nations, there are the Sustainable Development Goals, as we already discussed, with the antibiotic resistance problem in the focus. And in the United Nations, there are also a big activity called green procurement in the healthcare sector. And of course, the procurement is a very big issue in here. It also has to do with the falsified medications, but it also is a question of that if we are the United Nations is a very big drug buyer in the world market, and if they can follow the guidelines where these procurement processes also take into the consideration the wastewater problems and the ecotoxicity of these products they are buying, that will have a huge impact on this procurement systems in general. We have a joint WHO and United Nations environmental program where these problems are discussed and solutions are found. In the European Union level, we had last year, this time, the communication from the Commission to the European Parliament, the Council, and the European Economic and Social Committee about the European Union's strategic approach to pharmaceuticals in the environment. In our level, in FIP, there are the guidelines on good pharmacy practice together with WHO. And then we also have in FIP accepted the statement on green pharmacy practice, and we also have a big reference document where the statement then was sieved out. If we look a little bit closer to the EU strategy in the next slide, we see that they have these titles for the activities. And I'm sorry, this is a little bit EU-centered now, not because that's the area I know best. But I think these are the same issues in around the world, so it doesn't make big harm that we go look from this. So in this strategy, they have taken these things up. So first thing is that this is for both human and veterinary medicines, and it's the whole arch from production to waste. So you have to have this kind of a holistic approach to look at this problem, because these APIs are used in both in the human and in veterinary medicines, and the problems can occur in any phase of their usage, and even in the research. So what is the important thing? Number one is to raise general awareness, what we are doing here, for example, now, and promote prudent use. And the prudent use here means that the rational therapy, the rational usage. And the idea here is that we wouldn't produce any waste. I will later say a few words about this waste problem, but everybody understand that the rational prescribing, rational usage are very important to avoid excess waste. The next point they have taken up in EU is to improve training and improve the risk assessment. Training of the medical, pharmaceutical, etc. professions is extremely important, and the thing is that what we are doing here. And about this risk assessment, I already told you about how this is done, and the methodology is not very well developed, so we need really some activities here so that this risk assessment could bring us better results, and we could use it in a more effective way. We also had an urgent need to gather more monitoring data. As we saw in this picture about the world, what kind of medicines we found around the world, there were some gray areas, so we don't know really enough about this, what kind of molecules end up into the waters and what kind of cocktails they produce there, and what happens when they are there. There is also a need for green design. This means green chemistry, and we have an urgent need to reduce the emissions from manufacturing. And here the biggest problem are these different standards in different countries, and the GMP not covering this emission part at all. We also need to reduce waste with different ways, and we need to improve the wastewater treatment. And to really tackle this AMR, in Europe they have this One Health action, but globally we also need to take actions. So if we go to these different issues a little bit closer, in the next slide you will find what means by green chemistry, and how we can also see what we can do with the formulation part. So banning by design is this idea here. So you can change the molecule so that you couldn't have these active units here, what you see in this picture. For example, this Diclofenac. So you have these chlorine units. Could you use something to get rid of them so that the molecule is still active, but didn't cause all these harmful effects it brings with it? And with this, the other one example here is about the biodegradability. Could we use some kind of nano formulation so that we don't use so much medicine or active pharmaceutical ingredient, so that we will reduce the waste in that way? Next slide then. In the next slide, we can see how we can affect the wastewater management, and there are different possibilities in here. This is an example from a research project where the discussion about can we already get rid of the medical waste, for example, in the hospital level, instead of diluting it first and then sending it to the wastewater plant. The next slide tells about that the issue I already have mentioned several times. The necessary drug usage is the main factor in the environmental load. And for that reason, we need to have the rational prescribing, the drug waste management on the hotspots, and these legislative actions about the take-up programs, classification of hazardous waste, and consumers informed about the importance of the rational usage. In the next slide, I have put a picture of this classification, and I think I went through this. What is the problem is that this classification only goes for the APIs and then of this will be needed for this, for example, this price discussion. In the next slide, there is a picture of this green pharmacy practice document, which you can find in the FIP homepage. So just take your time and find the very useful information in there. And then I will use the last few minutes to discuss about this, what pharmacists can really do. We are working in the different parts of the life cycle of medicines. So I have put here the different things: drug development, research. So that's the applications of green chemistry in industry. There are the small emissions, effective processes and classification, wholesalers, effective logistics, and in hospital pharmacies there is the drug committee work where you can influence the procurement processes, education of the other staff, and collection of waste at point, and the risk management scenarios. In the open care pharmacy, the informing of the or trying to get the people to be adhere to their therapies, information to customers of their role in reducing the waste, and about the risk management things. And those of us who will work in the regulation, so there is a lot to do with the classification, with the drug pricing issues, with GMP, and with environmental regulation in general. In the next slide, I have put an example about how you can inform the customers about that the customers can make difference also in their life. So they can influence, and there is a need to influence because they can help to make their own treatment successful. They can reduce their own medical costs, and they also can reduce the environmental load. So this kind of posters and information you can give to the customers, and you can also work with the patient associations to inform them about this medical waste problem. In the next slide, there are this example about the risk evaluation and management in your own working place. So this means not only the evaluation of the APIs, but this is about your own processes, and then to concentrate on the actions which you have identified as causing the biggest problem for the environment. And if you are really interested on this issue, you can also seek for the certification for your working place, according to the ISO certificate or the WWF Green Office certification. And in the next slide, there is also a very busy slide, but there is a risk analysis chart from the community pharmacy where we have made, this is from my pharmacy, we made this kind of risk analysis. What are the things we are, in which way we are causing troubles to the environment? There's the paper usage, premises, storage, equipment, cleaning, eating, logistics, customers, etc. And we have found out that the most important thing we can do is to influence the effective medication usage, and by informing customers and the healthcare around us. So this is how you can find with these tools simply the ways where you can be the most effective in your own environment. And if we take the last slide, which is about the pharmaceutical education, so you can also, or what is needed is that we change our own education, and you being active students, you can also affect your curriculum, I think, and ask that you will be properly educated also in these environmental issues, not only in your pharmaceutics general knowledge, but also from the sustainable pharmacy practice, because we do have a lot of knowledge now, and so it's just needed to be educated to you, who are the future of our profession. So thank you. This was a little bit run through these things. I hope you are still alive there. And now we have some time for the discussions. Thank you from my part.
Thank you, Eva, for sharing with us your knowledge on how pharmaceuticals impact the environment and the cycle they undergo. I do believe it's very important for us as pharmacy students to try to break the cycle and to not only protect plant and animal life, but to also try to prevent antibiotic resistance from occurring. And today we were all presented with various solutions, and like you mentioned, we are the future, and it's my hope that every pharmacy student and recent graduate that attended is able to take some of these solutions and apply them, or even advocate for them in their respective countries. And I am now going to open the floor to questions as time permits. We do respect the time of everyone, and we'll try to conclude the webinar within the promised time. So the first question was from Maisa. She asked, how to collect data of the number of pharmaceuticals detected in surface water. Also, how long does that approximately take?
Yes, there is a lot of data collected about this and a lot of research going on, but and you cannot say any general number that how long time it does take or it doesn't take. So because these molecules are there, they just metabolite, or they can be also become smaller or particles or whatever, and then they lose of course their effectiveness in that way. But they unfortunately you cannot generalize.
Okay.
So each molecule is different.
Okay, and then our next question from Allison is, are there any global legislations for pharmaceutical waste?
No. The issue is that the waste legislation belongs to the environmental legislation in the countries, and the pharmaceutical legislation is global in a way because you have the GMP, but it's not legislation; it's just the self-regulation. But there is no international agreement on the waste issues.
Okay, thank you. And then our next question is from Lucia. She asks, moving forward, what do you think should be done to ensure that GMP on waste management, especially of antibiotics, is followed?
I think that should be first they created or we should be in agreement that GMP should also cover the wastewater management in antibiotic production, and from that then we could continue. Now this is not the case. As far as I know, WHO is working towards that direction, but our medical industry possibly is not so happy about that issue. So there are a lot of discussions needed on this. We have to work together in good collaboration.
Definitely. And then the next question is from Erica. Can wastewater management ensure total clearance of the APIs? And then the second part to that question is there any other method to treat the wastewater?
There are many ways you can treat the wastewater, and as I tried to mention here, is that possibly for these very difficult molecules, it could be better if we could treat them already before they end up into the waste, into the plant, so that we could, for example, in the cancer oncology clinic, we could use toilets where you can collect the cancer medications already on the toilet level. So there are a lot of techniques, and it's possible to get rid of all the molecules, but it's, for example, in the transferable osmosis. But these techniques are quite expensive. So the question is that where they are most effective. In Switzerland, they have a legislation where they say to this, if you have a wastewater management plant which is very close to the industries or so, they have strict regulations about that. They have to be able to reduce the amount of waste much more than those which are working with the wastewater management which is not that problematic. So this kind of could be an effective way to solve this problem.
Okay, thank you. Another question from Maisa is the measure of ecotoxicity part of the dossier everywhere in the world?
I don't know, I have to say. I know from US that it has been, and in EU it has added. About Japan, I would almost guess that it is, but not from the other parts of the world.
Okay, thank you. And then a question from Januka. What is the best method to dispose of medicines at home?
You have to bring them to the take-up program places. So because they are hazardous waste. So the first thing is that the medical waste should be classified in the national legislation as hazardous waste, and then you should bring them to the place where the hazardous waste is collected. Because if you put them down, flush them down the toilet, or if you put them in your backyard, so they will not vanish anywhere.
Okay, thank you.
This unfortunately is done in many parts of the world.
Yes, and then one last question from Sabita. The expired drug exposed and disposed of in the environment hazardly from the household, does this have the same effect as the unexpired one?
Oh yes, they do. It's the same issue. They don't vanish anywhere. So when a medicine is expired, it might be because its life cycle has ended, but it hasn't vanished anywhere. It just have possibly it has lost a part of its effect because it's not anymore in the level to be as effective as it used to be, but it hasn't vanished. It has metabolized some way.
Okay, thank you. And then our last question for this webinar is from Yasser. What affects most on bacterial resistance? Is it human misuse or pharmaceutical industry pollution?
I think it's a human, not misuse, but use, together with the industrial pollution. So there are many things which are causing this problem, and possibly the usage. For example, antibiotics used for fish treatment or something like that, which could cause a huge problem. So difficult to compare in such a way that who is more responsible than somebody else. So all these things has to be discussed, and we have to find out solutions together.
Okay, thank you. And we just have two more last questions that we can take, and then we have to conclude the webinar. So the next question is, how can we make the general public aware of the proper disposal? An example is in Nepal, where we don't have a take-back program.
I think there should be a pressure from the pharmacist side to first of all have the pickup program, because your officials also should be aware that these medicines doesn't vanish anywhere, and they will cause a lot of trouble when they end up in the environment. So this is a discussion of raising awareness in every level of the system. Unfortunately, in many parts of the developing world, where the regulation is very weak, it might exist, but it's never implemented. So this is not the first problem then but I think that your regulators in any case understand this antibiotic resistance problem, and for that can be used as a tool when you raise the general awareness.
Okay, thank you. And then the last question from Erica. She says, sorry to ask again, what can we do as a pharmacist, especially in industry, to minimize the waste products? Should we throw it in a special tank or mix it with some reagents to neutralize the hazards?
The only effective way for the waste is to get it to to burn it in a temperature which is over 1000 degrees. So you have to have a specific unit where this is done.
Okay. Thank you so much, Eva, for answering all of our questions. I just have a few slides to go over with everyone before we conclude. I wanted to remind you all of the future events for IPSF. We do have our World Congress, and we also have the regional symposia. If any of you are interested in going, please check that out. And then also we have our social media pages. We have Facebook, Instagram, Twitter, and then a recording of this will be posted on YouTube, so look out for that. And I wanted to thank Eva once again for joining us in this webinar and for sharing all of her expertise. I want to thank all of the members for joining and for registering, and I will